Hi everyone, and welcome to the next video in this series on respiratory physiology. The next set of videos is going to be about static mechanics of the lung. And so static mechanics is interested in static equilibria in which there's no movement, so the forces are equilibrated, and the questions that we're going to be asking ourselves are about the equilibrium volumes and the equilibrium forces that are at play. So we're not as interested in the time that it takes for things to happen. We're not as interested in the dynamics of the system, but we are interested in the static equilibria that come therein. So the first video that we're going to have here on this series is about compliance. And compliance is effectively what is the change in volume, or what is the volume that an object assumes when a given pressure is applied to it. And so we're going to kind of build that up. But in order to talk about compliance, we need to be talking very specifically about which pressures we are interested in when it comes to respiratory physiology. And so sort of bringing back our knowledge of the lung and the anatomy of the lung, we remember that the lung is encased with inside of the pleural space, right? So the pleural space is the sac, remember, that's attached to the lung here and kind of attaches to the lung in sort of encroaches and also attaches a little bit to the hilum, which is what I've left blank there, which is where the vessels will come out. But I want us to remember that when the diaphragm and when other muscles pull on the lung, they are pulling specifically on the parietal pleura, right? They're pulling on this outer membrane, and if you want a review of this, I did a video on the lung anatomy, so please take a look at that. But when the structures, the muscles that are pulling on the lung are pulling on the parietal pleura, and that effectively is causing the lung to expand because what is inside of the pleural space is an incompressible fluid. Now, in order to think about what is the pressure that is being used to inflate the lung? So the lung here is obviously being inflated by sort of the trachea, which is out here, and that kind of is feeding into the lung and is providing air here at atmospheric pressure, right? We've got atmospheric pressure air outside. But when we're talking about the pressure that is inflating our lung, we are really talking about what's known as a transmural pressure. So we're talking about the difference in pressure between the lung and the pleural space. So one way to think about this is if you tried to blow up a balloon in regular air, and putting some pressure into it, right? So you're forcing air out of your mouth and putting it into the balloon, you can blow up a balloon. But now imagine that someone is pushing down on the balloon from the outside world. It's going to be much harder to blow up the air. So in other words, it's not just the pressure inside this P1 that matters, but it's also the pressure outside that matters in terms of determining how the sort of forces at play, and also how large the lung will expand to. And so really the net driving pressure of inspiration is going to be a transmural pressure, which is, we're going to define that as delta P. And that delta P, or let's actually call it P transmural, PTM. Okay, so the transmural pressure is going to be equal to the pressure in the pleural space, P2, minus the pressure in the lung, which is P1. Okay, and so that's going to be the driving pressure of any sort of inspiration. Okay, so now we're prepared to talk about what happens when we increase or decrease this transmural pressure. So in other words, what happens when our diaphragm pulls down on the parietal pleura and our P2 then suddenly drops, right? Because now we're decreasing the pressure inside of the space, right? We're pulling down on the parietal pleura, and our transmural pressure then is going to increase, or it's going to become, there's going to be a larger transmural pressure because our P2 is now much smaller than our P1. And what that's going to do is that's going to effectively draw air in from the outside world. But where will the system equilibrate? In other words, how large will the lung get if we pull down with a certain amount of pressure? And that's the question that compliance allows us to answer. So in other words, it allows us to answer the question of, if we change the transmural pressure, in other words, if we change the pressure, P2 pressure, by expanding the pleural space, or not expanding because it's incompressible, but by pulling down on the parietal pleura, if we change the transmural pressure, what is the change in volume associated with that? So what is the change in the volume associated with it? What is the change in lung volume associated with that? And this is the definition of compliance. So let me write it like this, actually. So compliance, which I'll call C, is going to be defined as this. Okay? So the change in volume associated with a unit change in our transmural pressure. Okay. So what are the factors that contribute to compliance? So one thing to keep in mind is that compliance is actually very similar to spring constant, right? Because effectively it's telling you for a given amount of driving force, which is, this is kind of like a force, what is the change in volume, which is kind of like a length, right? So if you remember the definition of a spring constant, the spring constant tells you, well, if you have a spring here, how much, what is the increase in the force? If you pull the block at the end of the spring, if you pull it a certain length, what is the increase in force? So our spring constant is kind of inverted. It's, the spring constant is really change in force over change in length. But here it's kind of the inverted way. So this is kind of similar to 1 over spring constant. Compliance is kind of 1 over the spring constant. So when we start modeling the lung and we start talking about it as a spring, we're going to use that approximation. Okay, so what are the factors that contribute to compliance? So compliance. So when we think about the lung as a spring, we can kind of get some intuitive understandings of what those factors might be, right? So obviously the springy nature of the lung, in other words, what is the stiffness of the lung material? So we're going to say stiffness of lung material. And that's going to be related to a variety of things, right? That's going to be related to the density of the lung. That's going to be related to the tissue composition. And so we're going to talk a lot about different pathological states in which those might be affected. So emphysema, you have basically a de-densifying of your lung. So the compliance increases, the stiffness decreases, the compliance increases. In pulmonary fibrosis, you have the lung gets scarred basically, and you therefore have a increasing stiffness and decreasing compliance. But that's one factor. The other factor that I want to touch on is surface tension. So the first factor, the stiffness, I think is very intuitive. So I'm not going to harp on that point. But surface tension is the other factor that will determine the compliance of the lung. And so let's talk about why surface tension is involved here. So what is surface tension? So surface tension, remember, it can be defined in many ways, but one way to define surface tension is what is the change in energy associated with an increase in area of a fluid. So if you imagine you have a fluid, if you have some water, and this water is in a bubble shape, if you spread out this bubble, so why does water form a bubble is maybe the question that we're asking here. So if you spread out this bubble, and this volume is now into a puddle like this, right? Instead of being a bubble, it's spread out into a puddle. Then our area has increased. In other words, the area which is the surface area of this fluid has now increased. And why is that a problem? Well, because as so long as we have these intermolecular forces inside of this water bubble that are sort of kind of creating some sort of potential energy there, right? It's like a low energy state when everything is nice and tightly bound up, and everything is kind of interacting with itself in this little intermolecular forces. These water molecules, they don't need to interact with the air molecules, which they hate, right? The water wants to stay with water; it doesn't like air. So by increasing the area, this change in area is exposing the water to more air, and that comes at an energetic cost, right? This is a higher energy state. This is a higher energy state compared to this, compared to our bubble. So surface tension is basically a change in energy associated with a change in area, and we can see how if we have water now sitting in our lungs, which there is quite a bit of water in our lungs, and I'm just going to draw it like this as a little water wave, but you can imagine that it's actually water in small amounts of water in our little alveoli like that. That as we increase our area, that is going to obviously come at an energetic cost, and so the surface tension, let's call it tau, is the extent, what is the energetic cost per unit increase in area, okay? And so you can imagine that this is very similar to compliance in many ways, right? It's asking basically how much force, or what is this, or if you think about energy and force as being related here, right? We've got this, we're pulling a pressure and we're kind of opening up this, opening up our lungs, which is obviously a sort of higher energy state. We can think about this bubble, what's happening to these bubbles as we open up our lungs. Well, what's happening to these bubbles is that, the water, which was initially sitting in our alveolus, like, in a little bubble shape, let's say, it's sitting at the bottom of our alveolus, like this. As our alveolus gets bigger, that bubble is going to get spread out, right? That amount of water is going to get spread out over the wall of the alveolus, and it's going to have to, therefore, increase its area. So we can imagine why this energetic cost of increasing area is now going to contribute to the stiffness of the lung, right? It is going to contribute to the resistance of our lung. Now, I shouldn't say resistance because that has another definition, but it's going to contribute to the hesitancy of our lung to want to open up. Okay, and so why is this important? Well, because surface tension is something that is regulated in our lung by surfactant, right? So surfactant is this basically oil that our lung produces in order to reduce the surface tension and hence increase our lung compliance, particularly at low lung volumes. Okay, so let's explain what that means. So these are the two factors that are going to contribute to compliance, but you have to remember that compliance is not necessarily constant over the expansion range of our lung. So I mentioned that surface tension is particularly high. The surface tension forces are going to be particularly high when the lung is small, so when the lung is in its deflated state. So that means that our compliance can actually change over the size as the lung gets bigger or smaller. So it's, even though we can think about it as a spring constant, the spring constant can change as our spring gets more extended or contracted, which is not usually how we model springs. We usually model springs as having a single spring constant. But in the case of the lung, it is important to think about how the compliance changes over the lung volume. So at small lung volumes, the surface tension forces are higher. And so at small lung volume, I'll just say vol, at small vols, surface tension is high, and that contributes to decreased compliance. Okay. The other thing to keep in mind is that the lung the lung compliance is not necessarily state independent. So what that means is that if you get to a certain lung volume, so imagine you stretch out your lung and then you pull it back to an intermediate volume versus you just pull it to an intermediate volume without stretching it out much higher than that, right? So imagine you take your lung, which is like, let's imagine it as a spring now, and so you take it from here all the way out to here, and then you let it come back to some intermediate lung volume here. So if you go directly here versus if you go here and then here, it turns out that because of a property known as hysteresis, the lung compliance, or in other words, the stiffness of this spring, the spring constant of this spring, might actually be different if you go via this path versus via this path. And the reason for that, as you can imagine, is if you sort of loosen up your spring, right? You like give it a big tug and you kind of loosen up your spring like that, then your compliance will actually be higher, or your spring constant will be lower. Your compliance will be higher if you come via this route versus via just the straight route. And so that's another property of the lung, which is that if you take a deep breath and then you breathe out, the lung compliance on the breathing in and on the breathing out are different because of this memory capability of the lung tissue. In other words, it kind of remembers the fact that you just opened it up, and hence it is a little bit more compliant. Okay, so that's a brief introduction to compliance, and we're going to talk more about how this influences respiratory mechanics in the next video.